Do you know how to allow sharing? Because you see, on Zoom, if I start moving my slides, this will not be displayed on Zoom.
I can see it.
No, you can only see the first slide. Yeah. You see, I'm changing the slides, but
Right.
on Zoom, this is not. This is because it says that your screen sharing is paused.
Can I try resume share?
Um,
Green next to share.
it doesn't do anything. Yeah. You know, sometimes what happens is the following. Sometimes I just need to quit and connect again. No.
Maybe use a PDF file or sorry, let's see.
You know what? I can do maybe this because now it seems to be working. So if
maybe don't display, I think there is just a full screen. Don't display. Maybe just like a view, full screen, so view.
view.
Full screen, so and get the source screen. Yeah, that's good.
Okay.
Yeah, maybe there's a
Can we get rid of this thing? Okay, perfect. I think as good. This is as good as it could get. Okay, so.
You might turn on the volume in case people speak on your end.
Sure. All right. And let's see. I wanna.
And also probably the video. Video.
Oh, should I also? Okay. Okay.
You ready? Thanks everyone for coming. Today we're happy to welcome Mikhail Ivanov from MIT, and today he's going to talk about love and naturalness. So please join me in welcome.
Thank you. Thank you so much for having me here. So I assume that everyone can hear me okay? All right. So yeah, I'm going to present some work that I've been doing in collaboration with various groups of, well, several groups of people, mostly Sergei Dubovsky, Julio Para-Martinez, Panos Charalambos, and also a group of junior collaborators, students, Saket, Zihanjo, and usually, all right, usually is doing his postdoc at Princeton. All right, so my talk is going to be about black holes. Okay. Okay. It's going to be about black holes. As you know, that we're witnessing a revolution in gravitational wave science. Over the past several years, we have seen many many black hole binaries and individual black holes as a result of their mergers. And this impressive experimental achievement, it also poses some theoretical questions. The most urgent one is probably whether our theoretical tools are good enough to understand the behavior of astrophysical black holes that we see in the gravitational wave detectors. And maybe another another interesting theoretical question that I can ask is, maybe now it's a good time to try to understand the origin of hidden symmetries of black holes, because black hole studies, the studies of black hole perturbations, this is something that was a hot topic in the 70s, in the 80s, and then people have discovered many hidden symmetries of the black hole perturbations. And now, given that we're actually measuring, we're seeing the black hole perturbations in real life, maybe now it's a good time to understand these hidden symmetries. When we typically talk about a gravitational wave merger, there are three regimes. So typical merger goes, well, starts with the inspiral phase where you have two bodies. So they're inspiraling, they're losing their gravitational energy, then they coalesce and merge. So there is a merger stage. And then after that, you have some stable state, or typically it's a black hole that is sort of, oscillating around some equilibrium point and is going towards like more equilibrium stage where these oscillations decay. So as you can see, these three different stages that we can observe, they're sensitive to different physical effects. For instance, when you have two bodies during the inspiral phase, you can actually probe the tidal deformation of the sources. And this is one of the channels that you can use to understand the internal structure of these bodies, to understand, let's say, the equation of state of them. And in the opposite part of this spectrum, when we observe the outcome of the merger, we see some black hole oscillating around some equilibrium point, and those oscillations, they correspond to the so-called quasi-normal modes that, well, they have a lot of profound features. So it's a totally different regime that is interesting. In my talk, I'm going to focus mostly on this regime, on the inspiral phase. And this regime is cool because we're actually sensitive to the nature of the compact objects. And well, this is because, again, the typical problem during the spiral phase is that we have two bodies that are orbiting each other. They tidally deform each other. And there are several effects associated with that. First of all, their shape will be different because of the tidal forces. And second of all, also there will be some tidal heating effects that are dissipative. So there will be some exchange of energies between these bodies. And like a typical outcome of this tidal heating exchange is the tidal locking. So at some point, because of dissipation, well, we know, for instance, that the moon is tidally locked, almost tidally locked with the Earth, right? So this happens because of the tidal heating. And these two effects, they change the waveform in different ways. So the tidal heating effect appears at the 2.5 post-Newtonian order, so it changes the waveform, let's say, at some earlier stage of its evolution. And then the conservative deformation of the surface of the compact body, this is something that happens at 5 post-Newtonian order. So this is something that starts affecting the waveform noticeably closer to the merger phase. And these two effects, they, tidal heating and tidal deformation, so they have been studied a lot in the literature because one can use them to probe the internal structure of these bodies, as I mentioned. Well, basically, a lot of the, at Legion order, the gravitational waveform is not sensitive to the exact nature of the compact body, right? It's only sensitive to the masses. And it's only at these higher post-Newtonian orders that you can say something about the, let's say, equation of state of a neutron star. So these conservative tidal deformations, they have been, they attract a lot of attention, specifically in the context of measurement of the equation of state for neutron stars. But in principle, you can use them for other things. So you can use both these conservative and the dissipative effects to test the nature of compact objects and, for instance, to search for exotic compact objects. We have done this study recently with Hongchen Chi and Zihan Zhou. So basically, we assumed that all black holes at the LIGA, Virga, and Kagra experiments that they have observed, that those correspond to some sort of exotic objects that are similar to black holes. And we try to test whether it's a good assumption that they're actually black holes. And from this kind of scaling, you can understand that actually this tidal heating is the leading order effect that will tell you whether the body you're looking at is a black hole or not.
Good question.
Yes.
Sorry, I'm not familiar. So, is this oscillations some of the mode from expanding the matrix to and some elevation h? And is that the kind of like a longitudinal mode or like what kind of mode is this?
Well, this is a strain. This is like a sum of the two contracted with the detector response function. So this is like the overall, let's say, fluctuation of the length of the detector. So it's a combination of the two, right? So because we're talking about gravitational waves, so this is really the age of the gravitational wave emitted during the in spiral phase. Right.
So, Misha, what is the difference between the tidal aging of Playfors and neutron stars? Is there a qualitative difference?
Well, I would say from the post-Newtonian perspective, there is no difference. Just, the body has some internal structure, has some internal degrees of freedom that could be excited by absorbing stuff. In the context of black hole, the physical picture, like more microscopic physical picture, is that, well, we know black hole just absorbs stuff. So black hole can absorb gravitational waves, right? So that's why you will see at LIGO, you will see less gravitational waves, and their phase will be different. Now, in the context of neutron stars, this will correspond to, neutron stars have some, equation of state. Let's say there's some fluid associated with that. There is some, density, and there is some viscosity. So that will dissipate the gravitational waves due to viscosity. So maybe microscopically slightly different. In one case, just black hole absorbs everything. In the other case, there is actually some microscopic viscosity at play. But in terms of its effect on the gravitational waveform is going to be the same. Okay.
So how will, if it's the same, how will, is that you can differentiate?
Yes, because the exact value of how much you absorb will be different. For neutron star, this will depend on the equation of state. For black hole, there's a jar prediction. Well, actually, this is subject of my next slide. I just put there. Yes.
Yes, because I'm asking two slides back.
Okay.
If you this think of the solar mass in a logarithmic scale in the vertical axis, and then what's the what are they corresponding to you shown here? So what's the horizontal axis? The vertical is the
the horizontal axis just nothing, just tells you number of the event, let's say, right? So this event 1, event 2, event 3, so it doesn't have any physics associated with that, right? So the only relevant physical dimension here is the mass. Right. Any more questions at this point? Okay, yeah, maybe answering a little bit your question, Uri. So I'm going to talk a lot about this worldline effective field theory that provides you with a consistent definition of tidal effects. So basically, we can constrain the Wilson coefficients of this effective field theory, and they will tell us something about the nature of compact objects. So we did this first search, first constraints on tidal heating of black hole-like compact object, or black hole mimicker, sometimes they're called, from the data. And basically, those are the actual, let's say, best fit strains that from our, strains from our CMC chains. And here you can see constraints. The most, physically, clear quantity that you can define is the ratio of the energy of gravitational waves absorbed by the compact objects versus the total energy emitted to the infinity. And well, we see that our results are consistent with 0, so we don't observe any deficit. And there is a black hole prediction here shown by the dashed line, and it seems to be closer to 0, but it's actually offset a little bit. So in terms of the usual, in usual jar, there is a threshold, like there is a guaranteed value of delta EH over delta E emitted, which is around 10 to the minus 4. So like 1 part in 10,000 in terms of the energy of emitted gravitational waves actually gets absorbed. But in principle, if you have some compact-like mimicker, it could have also some equation of state, and could have some viscosity, so you can absorb more, and we have constrained this absorption.
And also the data, the blue is data, right?
Yeah.
It looks very noisy, right?
Yeah.
So what's the?
Yeah, well, you need to go through all this, phase from the match filtering analysis, right? You need to. Okay, this is only an illustration. Like the actual analysis that you do in terms of the, waveforms in Fourier space. So, okay, good. So now let me say a few words about this other tidal effect, the tidal deformations. They are parameterized by this parameter lambda that is called the log number. I'm going to show you the formal definition on the next slide. So here I'm just showing you the plot of the constraints on the equation of state of neutron star from the neutron star merger, GW170817. And again here, well, you can see some allowed region of these values, so you can rule out certain models for the equation of states. So this is how we use the tidal effects to learn the nature of compact objects in gravitational wave astronomy. Now, how these effects are actually defined? Like, let me give you a more concrete definition and start with Newtonian gravity. So in the context of Newtonian gravity, they're called Love numbers, these tidal deformability coefficients. They were introduced by a British mathematician Love. And basically, he considered the following problem. Imagine that you have compact body, so that is a fluid sphere. In the absence of any forces and external perturbations, it will take a spherical shape. And then if you have some external perturbation, let's say satellite, this will deform the body, right? So the unperturbed potential of, let's say, a test point measured here with respect to central body will look like minus m over r. So I'm assuming g equals 0, sorry, g equals 1. So this will be in the absence of any perturbation. Now you have a perturbation, then we can write down multiple moments. So if we want to describe the correction to the gravitational potential that our test particle feels here, we can write down basically the tidal force. And then this tidal force will also act on the central body, and the central body in response to the tidal force will scorch a little bit, and it will develop some quadrupole moment, and this quadrupole moment will also gravitate and produce a contribution to the Newtonian potential. So this is the total kind of expression at leading order to the total gravitational potential of this perturbed problem. And well, typically these kind of terms that we write down as powers of R, well, because we kind of Taylor expanded the gravitational potential of the satellite, so they will be powers of R. We call those terms tidal sources, and then the tidal responses, they will look like something divided by R, right? So those are the usual multiple moments of the central body. And in principle, this picture we can generalize to higher order multiples. So we can go to so this was for the quadrupole, the usual tidal force, but then we can go higher order multiples, octupole, and so on. And now what Love basically considered, he said that in linear response theory, somehow the amount of the squashing of the central body in response to the external field should be linearly proportional to the external tidal field itself. And the coefficient of proportionality he called just number, and then people after him called Love number. And here I define this number in a dimensionless way. So I specifically accounted for the difference between the tidal field and the induced quadrupole moment. All right, so this was the original definition of the Love number. But of course, since I'm talking about GR, since I'm talking about LIGO and gravitational waves, you might want to question the adequacy of this definition, in the context of gravitational wave mergers. Because, when we talk about events at LIGO, we look at black holes that, they are in the regime of strong gravity, they perturb each other. Why would this Newtonian definition make any sense? All right, so the idea, yes.
So the Love number can be positive, can be negative.
That's right.
Yeah. Did you explain there if it's positive, negative? Just make sure I get some intuition. I probably you explained that, but I just didn't get it.
Well, yeah, whether it's negative or positive, we'll define this a little bit like, okay, let's do an even simpler problem. Imagine that in the context of electricity and magnetism, you have some body, let's say a conducting sphere, right? And it has some external field. We'll put the external field, and the electrons will distribute and produce some internal dipole moment, right, in response to this force, right? And then whether you have this susceptibility, could be in principle positive or negative. Normally, it's it's defined such way it's positive, and it's positive. It means that the internal field will cancel the field inside, right? But you can also enhance. You can imagine a situation when the internal field enhances the external field, right? So this will correspond to, in my definition, to negative Love numbers. So in other words, like you can either think that the quadrupole moment like is aligned with the external tidal field or anti-aligned, and normally it is aligned, kind of same way with the minus sign. It's kind of anti-aligned, in this picture with the dipole, right? Normally it wants to cancel the field, so it will also want to cancel, right? So this corresponds to positive Floch number, and in other situation where the tidal field is enhanced, will correspond to a negative Floch number. In fact, for black holes, if we'll talk about higher dimensions, they can be both positive and negative. So at this point, I don't really have a good intuition why they should be positive or negative. But like physically, I can tell you that this exactly corresponds to the alignment or anti-alignment with respect to the tidal force.
And the Floch number is labeled by another subindex is L.
Yeah, which
is some integer.
Yeah, that you can define. So this L basically tells you what the quadrupole. Okay, L equal to is 2 for quadrupole. Yeah, is basically just telling you the multiple moment.
It needs to be even.
Yes, it is even.
Okay.
Yeah. Sorry. No, it has to be integer, right? Because for octopole, it's L equal 3. It starts with 2, right? You cannot have a dipole or monopole in GR. Type of force starts with the quadrupole, but then you can have quadrupole, octopole. You can have L equal 2, 3, 4, and so on and so forth. So it's an integer higher than 2. Okay.
Not 2, so 3, 4, 5.
Well, for the quadrupole, it's 2. Yeah, 2, 3, 4, 5. Yes.
Yeah, when we have like the R squared EIJ term, it's like the scalar expansion is valid around, or it's like accurate around R equals 0, but
Yeah.
then around R equals 0, the multiple expansion is not it's like close to infinity. So where like when we write down I to the like Taylor plus multiple, where do we think of this approximation as being valid?
Oh, it's valid as long as your test point is close to central body. It will break down when you reach the satellite, right? The source. You can think of this source, it will say it has 1 over R potential. And now you just expand this 1 over R around this point, and this is how you generate a multiple expression. Any more questions?
So which QL will you consider? The L is equal to.
Well, mostly I will focus on the lean order on L equal 2, the quadrupole moment. But many of the results, well, actually, most of the results I'm going to present will be valid for any L. But in the context of gravitational wave astronomy, like you can only measure this one, because you can also think of this in terms of multiple expansion, that this, higher order multiples, they also press like 1 over R. So, and in the post-Newtonian regime, 1 over R is V squared, right? So each of the higher order multiple will be more and more suppressed in the post-Newtonian scaling. All right. So if you want to define Loft numbers now in full general relativity, okay, it's not an easy task. I, in principle, want to use a definition that matches the Newtonian one on large distances, right? But then we also want this definition to respect the symmetries of GR. So want to be reparameterization diff-invariant. And also one can, well, obviously, GR is very nonlinear. So one may wonder whether, this, the nonlinearity of GR can break this story about the split of the tidal field into, well, split of the gravitational potential into the external field and response, or source and response. So this is something that makes sense in linear theory, but maybe in nonlinear theory doesn't actually make sense. And spoiler alert that, yeah, in the future, we'll see that, yeah, indeed, that this split doesn't really make sense. So the split is not well defined, and the tidal field and the response, they mix. And this is something that will produce the logarithmic running of Loft numbers. And so the approach that kind of takes into account all these points is called the worldline effective field theory, developed by Goldberger and Rothstein around 20 years ago. So the idea of this worldline effective field theory is that we can split. So our problem, having a body that's tidally deformed, part of the binary system emitting gravitational waves. Each part of this problem we can break down into its own thing, and we can then in each of the regime, when we focus on a single deformed body, or whether we consider the orbital motion, or whether we consider the emission of gravitational waves, in each regime you can work out a systematic Taylor expansion. And basically in the ET framework, we disentangle physics that operate on all these different scales. And we do perturbation theory around each appropriate scale. So in the context of the tidal effects, the relevant scale will be the size of the body, let's say the Schwarzschild radius. And then the orbital motions are controlled by the potential modes. So whose typical scale is 1/r. And for radiation, the typical scale is the wavelength of the radiated gravitational wave, which is much greater than the size of the orbiting system. So you see that normally we have this hierarchy of scales. So we can systematically calculate the waveforms by taking into account all these three different physical regimes. And basically now in my talk, I'm going to mostly focus on this first part, on the effective field theory description of the single gravitational body itself. And the idea then is that if I focus on this regime, I'm looking at the distances much greater than the size of a compact body. In this context, I can work out systematic description of gravitational effects by perturbing my point particle action. So on very large distances, when my distance is much greater than the size of the compact body, it will look, no matter what it is, it will look like a point particle, right? So its action will be described by this action will look like this, minus MDS. And then on top of that, I can write down some multiple moments that will take into account some non-trivial finite size structure. So this is the idea of the worldline EFT.
Remind me, what's the scale of RS?
So RS is the Schwarzschild radius, right? So 2 or c squared, if you do c squared. Okay.
So when you compute the block number, you like also previous slide, you have the RS. Do you imply there is already a black hole? Does it require that?
No, I don't have to require it. This is just my definition because mostly I'm going to be talking about black holes. But you can define, well, typically you should define it with respect to the size of the compact body, right?
Right.
Like for neutron stars, their typical size is greater, like 10 times the Schwarzschild radius, right? It's only because, I already know that I'm going to be talking about mostly black holes. Yeah, I have some slides that describe this worldline EFT in some simplified settings. For instance, you can play this game for the electricity and magnetism. You can say that I have some charge distribution and imagine that I have some long wavelength electromagnetic field, the gauge potential A mu. Then I can describe this charge distribution by multiple moments. So I can start with monopole, dipole, quadrupole, and so on. And basically, in this worldline EFT, I can write down the effective action that starts with the point charge term, and then I can write down higher order terms. For instance, the first non-trivial worldline operator will look like this. U mu is the forward velocity of the particle, and in the particle rest frame, this operator will be just proportional to E squared, right? And then I can, write down also higher order operators, and this is how I capture the finite size effects.
All right.
Yes.
Go back with particle. Do the same thing.
Yeah, you can do the same thing you can do the Pauli coefficient, right? So for massive particles, you just replace this with the Pauli coefficient. Yeah. Right. Okay. So and now, in the context of this worldline EFT for electricity and magnetism, for instance, if I consider a distribution of charges, collection of charges whose net charge is 0, then the leading order operator will be just E squared. And if I supplement this action with the usual Maxwell term, then I can I can imagine many problems and solve them. One of them will be the response problem. So imagine that this A mu is an external field. Let's say we generate some external electric field. Then I can calculate, can do some simple response calculation with this action that is described by this diagram. I have external field, and the word line will produce some response. So the total field, after I calculate the response, will look like this. It will have the source term, and also it will have a response term that will look like chi over r cubed. And this is so as you can see from here, this looks like the electric field generated by the induced dipole moment, right? So in other words, this action, this word line operator describes the induced dipole moment. And chi, the Wilson coefficient here, is the usual polarizability coefficient. All right, so in the context of this EFT, worldline EFT provides you with a very neat way to describe the usual Maxwell, well, the usual effects that we're familiar with in the context of E&M 101. So at this point, you can say, okay, well, why do I need this stuff anyway? Because I can also solve everything using Maxwell equations. Well, in the context of E&M, yeah, this is true. But for gravity, we cannot solve gravity exactly. So this worldline AFT, maybe in many cases, is the only tool that we can use to calculate, let's say, the response problem. So if we want to include gravity, we should basically follow the same pattern. So we start with this point particle action, and then the leading order operator that is non-trivial is going to be proportional to this gravitational electric field, E mu, which is the Raman curvature appropriately contracted with the for velocity. And this is something that in the Newtonian limit will give you dj, di, dj phi, just the usual tidal field. So in the Newtonian limit, the action will look a lot like the action for a scalar field. So if the gravity were scalar, this would be the worldline action for gravity. But in principle, well, you should really always remember that whenever you see this combination, it all comes from a diff-invariant quantity that, well, basically it's all generated by the Riemann tensor. All right. So now, in terms of gravity, we can use our worldline AFT to perform a similar response calculation, just like we did in the context of E&M. So we start with our worldline action. So we are going to use the Newtonian gauge for this calculation. We can again assume that there is some source. So we have some external gravitational potential, and then our worldline with this term will produce a response. So we can calculate the response, and it will look exactly like the Newtonian result. So there will be some, well, basically tail. So this is the external field. It goes like R to the L, and then there will be a response that goes like R to the L plus 1. So altogether we have 1 over R to the L plus 1. This is the usual Newtonian result, right? So we got this response tail as we should. And from the identification of this result with the Newtonian calculation before, we can say that the Wilson coefficient here is basically the Loft number. And you can see that physically, basically it plays the same role as the polarizability in the context of A&M. And from this, you can conclude that in principle, this worldline AFT gives a consistent, unambiguous gauge-invariant definition of Loft numbers because they just correspond to Wilson coefficients in the AFT. And you can define them by doing the matching calculation. So in the context of this worldline AFT, well, basically, as I said, this worldline AFT works for scales greater than the size of the body, right? So this is our AFT. And the full theory will be jar. So jar can describe jar can describe both the large scale motion and also the internal dynamics of compact bodies, right? So in our context, jar is actually a UV theory. And an example of the matching calculation that we need to do to define a Loft numbers is to calculate the same quantity in jar and EFT and match. And for example, if you want to match the gravitational potential, well, you can calculate the metric component G00 in the local asymptotic rest frame. So this is something that generalizes the gravitational potential in jar. So you get some jar expression that will look like this. Then you can compare with the EFT expression, and then you deduce that B is equal to lambda 2. So this is how we define Loft number. Well, rather how people used to define Loft numbers in practice. And once you have matched lambda 2, you can take advantage of the universality of the EFT. The same theory will be applicable to any phenomena that operate on scales larger than the size of the compact body. So if you extracted lambda 2 from the Newtonian calculation, you can then use, for instance, you can use the same number, the same Wilson coefficient to predict other observables like the waveforms, or another observable that you can neatly predict will be the scattering amplitude. Well, in fact, I'm going to argue now that if you want to extract a lot of numbers in a manifestly gauge-invariant way, you have to use the scattering amplitude. So I'm going to double down. Not only I'm going to say that you should define Loft numbers only using worldline AFT, but also if you want to measure them, the best way to do it is to extract them from the scattering amplitude. Because as I said, one can use in principle within EFT any observable to match, right? One can calculate the Newtonian potential, but the Newtonian potential depends on coordinates. So in the context of EFT, the Newtonian potential is the off-shell line point function. So it's not trivial to match. One has to make sure that the gauges that you use from both calculations are kind of consistent. In principle, one can define a very appropriate, nice frame where you can read off the tidal moments from the 1/r expansion, as we do in Newtonian physics. But then it's not obvious, and yeah, this was done in the GR literature, in particular by Eric Posson. But then it's not obvious how to translate these results for other observables. For instance, if I did some matching in some particular frame and obtain that the Love number is 0, does this mean that, for instance, the effect for gravitational waves will be 0 as well? So if you do some matching in particular coordinates, this coordinate sensitivity will be an issue. So it's not obvious how to translate these results. So in this sense, I'm going to argue that there is a better way to match. There is a better alternative, is to match the gauge-invariant quantities, such as the on-shell scattering amplitudes, because in this case, if we obtain some result, this by definition doesn't depend on any coordinate shifts, right? And if, for instance, if I did some matching from a scattering amplitude and I obtain that the Love number is not 0, that also means that automatically my waveform will have the corresponding term in it. And yeah, by this virtue of universality of EFT, once Love numbers are matched, I can compute now my LIGO gravitational waves.
Sure, just a quick question.
Yes.
The DL, so what kind of a Love number is it?
Oh, this is dynamical Love number. Yeah, I'm referring here to some okay, let's say an argument that I have with JAR people. Well, basically, there were some claims that the leading order Love number. So there was some back and forth, but people now are sure that for Love numbers, so for black holes, the Love numbers are 0, the leading order. But the next leading order, called dynamical Love numbers, is like a subject of debate, because there were some JAR calculations in some particular gauges that basically claimed that the dynamical Love numbers are 0, whereas for scattering amplitudes, I've obtained that they are not 0. And I would say that we need to use this effect. We need to include these effects in the gravitational waveforms. So this is the reference to this current, let's say, ongoing argument in the literature. So dynamical Love numbers.
Question, Zach.
Yeah.
Seems like the form to extract Love number or the synthetic field theory on the Wilson line, you require some scalar potential phi, right? Is it the phi is the scalar potential, some computational scalar potential? The phi.
Yeah, well, you can.
My point is that that maybe just part of the component in the energy momentum tensor, and the form you write is not quite fully invariant on the maybe Lorentz transformation. So probably, is there some kind of more proper way to write this way?
Oh no. Well, here of course you start. Yeah, you define with. You start with some T mu, and actually, if you want to describe everything, okay, this is something that you can do, but in the EFT, this is not a good language. Yeah, you need to use the T mu, and you need to use to define. Also, it's best to describe gravity using the Landau-Lifshitz-Seeler tensor. But yeah, what you do here is you start with some T mu, you fix a gauge, you calculate the tidal force, and then you calculate the response to this tidal force. But in principle, you can skip the first part and just say, look, imagine I already have some mass distribution that produce a given tidal force, right? In the gauge that I fixed, in the Newtonian gauge in this case. Okay, what is going to be the response in this case, right? In principle, you can match non-gauge invariant quantities. In the EFT, it's also fine, right? It's less maybe conceptually clear, but you can do that. So this is what I'm doing here. Yes.
So suppose you try and compute the amplitude, how would you show that the definition from the worldline is unambiguous? Isn't it subject to field definitions and the parameterization of the worldline?
No, well, field definitions is, yeah, that's a very good question. Thanks. Yeah, because here you can see in principle this expression. So I always define this as a coefficient in front of some operator. Now, if I start messing up with my fields, I start changing them, this will affect the operator part, but the Wilson coefficient will stay, right? So this is something that's totally unchanged, and this is totally invariant with respect to the
If I
field.
change the requirement when you're using some proper time.
Oh, you can use any other, you can go back and you can use any other worldline parameterizations you want, because the original, very good. So this is what I started with. This is what you should start with. You should introduce some general arbitrary affine parameter and the forward velocity with respect to that parameter, and then you should write down the quantities that are invariant with respect to the arbitrary change of this reparameterization variance, right? It's about that. Sigma prime is a function of sigma. So this action is manifest invariant.
So you can write that parameterization invariant action for any multiple.
Yeah, you just have to divide by square root of minus v.
If you redefine here, somehow you cannot redefine the field so much as to change that sympathetic space. Like you would not redefine the field by a scale.
Yeah, I would say that in the end, you can define, you can change your fields as much as you want, but this action, well, if you restore u here, you will see that this action will be invariant. What?
The higher ones.
Yeah.
Change.
Yeah.
Those will change.
Yeah, this will change, but in the EFT, as we know, the field, when you calculate scattering amplitude, this is a gauge, well, this is gauge invariant and also field definition invariant object, right? So this is exactly the point that I'm sort of trying to make here, is that if you use scattering amplitudes, then by construction, you can use any field choice as you want, but the scattering amplitude will not depend on it, right?
That's why my question was, what if you can't compute the amplitude itself? I feel like that's proof that this thing is an actually invariant object.
Right. Well,
we can match it immediately to amplitude, but a priori, just by looking at the worldline EFT action, which is subject to field definitions, it's not like evident to me that it's completely invariant.
Oh yeah, it's like any action, right? Any action is not a fundamental quantity. It's the only tool to calculate things, but the scattering amplitude is in some sense a fundamental quantity here, right? So that's why, again, that's why I'm arguing that, before, basically, people, they used to match the gravitational potential. And as I said, like this whole method is not really well defined. But if you start with any action, any parameterization that you want, you define a Love number as some Wilson coefficient, and then you calculate the scattering amplitude, and they should fix this. And if you want things to be maybe cleaner, you can, fix some set of fields. So you fix this parameterization, and then you use the same action to calculate all of your observables in a gauge-invariant way. So you calculate the scattering amplitude, and you calculate the fluxes for gravitational wave astronomy, right? And your result will not depend on your choice that you made for the parameterization of these fields.
It's interesting because, the action is not guaranteed to be ambiguous, but we usually use the action to compute concept quantities.
Right.
You can read out the symmetries from the action. So I guess if you tell us about another way to read the symmetries, that doesn't really rely on time and effective action. So perhaps we can read out immediately from the amplitude.
Right. Okay. Yeah, that's a whole different story how the symmetries get imprinted, especially these hidden symmetries get imprinted all the amplitudes. But here at this point, again, it's just we have a tool that at least can give us the results in a gauge invariant manner, right? So we can calculate the waveforms and can extract the relevant low energy Wilson coefficients in a systematic way. So this is the point that I was making. Yes.
What is the
Oh, this is the size of the compact body. So this comes back to your question. So in principle, we could use. So you can define this using the Schwarzschild radius, but in principle, for a generic compact object, this should be the size of that compact object. So this is just, I use dimensional analysis to restore to define this coefficient in such a way that lambda2 is dimensionless. Okay. So this is just dimensional analysis. Yeah. Well, our menu lambda rho depends on, in components, it depends, of course, on coordinates. But when you contract it, so R menu lambda rho squared is an invariant, right? Spiritual invariant. What's that?
The radius.
Oh no, you define it again. If you divide it by square root of minus u squared, this will be invariant with respect to the different parameter. It's going to be a reparameterization variant, right? So I just skipped this point that, you have the square root of minus v here, but you should also have it here as well, right? Okay. So here, in other words, I already chosen some worldline parameterization, but you can always go back to the original action that is fully invariant and make a different choice if you want. All right. So are we good here? Any more questions? All right. If not, yeah, let me say a few words about the scattering amplitudes. So again, let me go back to the electromagnetic case. So in the context of E&M, the same action that I introduced before describes the scattering of light of neutral atoms, such as nitrogen in the air. And entirely from the structure of this linear order operator, we can extract the three-level amplitude, and you will see that it will be proportional to the polarizability, or Wilson coefficient, times omega squared. So the amplitude grows with high frequency, and hence the skies are blue. Okay, this is the standard story that we use. Now, in the context of gravitational waves, we can consider the exact same problem. We can consider the scattering of gravitational waves now off our worldline, off the compact object. And then, well, in this case, you cannot quite ignore the massive part, but then the story is the same, that there will be a contribution to scatter amplitude from this operator. So you'll have a three-level diagram that will look like this. And EFT already gives you immediately what the scaling is. And you can use basically now the scattering amplitudes to match the coefficients in front of, the coefficients of this operator. And in GR, this amounts to performing a matching via Raman scattering amplitudes. So the scattering amplitudes have to be Raman because we know that compact bodies, like black holes, they absorb stuff. So the scattering will be fundamentally inelastic. But maybe, if you want to, for instance, focus really on this operator. So this is a local operator, right? So it comes out from the elastic part. So we can separate, in the, let's say, partial wave expansion, we can separate we can focus on the real part of the scattering phase. And we can then calculate this using the post-Minkowski expansion in powers of G. So linear order in the three-level scattering will actually be dominated by the point particle terms in this action. And just because of the scaling that I introduced before, so you see this scales like omega to 4, and the coefficient here is r to the 5th power. So r is rs proportional to g. So this is g to the 5th power, right? So this is a fifth post-Minkowski order. So that will mean that this coefficient will become important. This diagram will become important only very high in the post-Minkowski expansion. So the lowest order diagrams will be all eliminated by the scattering of point mass of the usual worldline. So the idea is that we can calculate the whole diagram in EFT and then match to the known expression in general relativity and extract the left number. Now, as I mentioned, there will be it will not be easy just because you need to go to very, very high order in post-Minkowski. So you need to calculate for loop diagrams, which are hard. But then there's a trick that you can use to get around. So you can, as I mentioned before, the contributions from this local counterterms, they will scale as the radius actually to the power of L plus 1. So if you go to higher dimensions, this will have a scaling different from the post-Minkowski terms. So the post-Minkowski expansion scales like powers of G, whereas the finite size effects will scale as some non-integer power of G in higher dimensions. This is because the Schwarzschild radius doesn't scale like G in higher dimensions. So in higher dimensions, you can actually easily separate it to contributions. And if you have the full scattering amplitude, you can read off this coefficient right away without having to compute all these higher loops. But then, yeah, we can go in higher dimensions to make this non-integer, but we can do another trick. We can use the Gribov-Rosart approach of analytical continuum angular momentum that will basically do the exact same thing, right? So if analytical continue L and say that L is not integer anymore, this term will not mix with the post-Minkowski expansion. So and this you can do already in 4 dimensions. So this is a simple mathematical property that you can use to do the matching. So basically the full amplitude in GR will look like this. This amplitude in the EFT, and then you can easily isolate you can easily isolate the finite size contribution, and then you can match it to the exact same amplitude in jar, and then you can extract the coefficient lambda 2 easily. So we use this for our trick before. It's not super straightforward, because sometimes there are singularities in the limit where L goes to the physical number, where L becomes integer, but these singularities, they kind of only appear in the case where there is where there is divergence in the loop diagram here. So there will be divergent part of this counter term that you need to include to normalize this diagram. So you will find these divergences here. So you need to properly interpret them. Yeah, but in principle, you can use this trick to extract it. You have a question, Johan?
Sorry, is it really extracting quantum effect here?
No, there are no quantum effects here. I consider pure classical problem. Okay. That means in the context of EFT, basically, I'm calculating my, I'm using the full kind of jar quantum field theory machinery to calculate the amplitude, but then I set to 0 all diagrams that have H bar in front of them. This is the easy way to think about this. So for the elastic scattering, this is what I'm doing. So in EFT, we do kind of full quantum gravity with H bar going to 0, and from the jar side, we just have the classical scattering amplitude from previous jar calculations that we can use to match onto. All right. Yes.
Does it mean that if you assume there's some analytic expression in the complex angular momentum plane, how do you analytically compute exactly? Because we know there are regular poles and all kinds of similarities in when one cell is not an integer.
Yeah, here, well, we don't need to, okay. Here, what actually happens is the opposite. It's when L is integer that you can have poles. Where L is not integer, you will not have any problem.
I don't say that the real line, but you also have poles in the complex.
Yeah, here if you assume that L is generic, to do this matching, you just assume that L is generic, and then you don't run into any problem. You will have issues will arise only when you take the limit where L takes, is integer, takes the physical value. But it doesn't happen like there is absolutely no problem at leading order. There is no problem, and this is because there are no logarithmic divergences. So there are no divergences in the post-Minkowski diagrams. So yeah, in principle, you should be careful, but yeah, here it kind of works. You can also calculate these things without using any tricks, and this is something that we did with Julio and other collaborators. We calculate the full Raman amplitude, with as many loops as you want. Well, we did 2 loops, which was sufficient for the lowest order matching. And then when you have the full expression for the amplitude, you can match the jar, and then this is conceptually very, very clean, and there is absolutely no ambiguity with that. All right, so now, I introduced all this, general approach and how we do these things. Now, before we do this matching, our general expectation based on dimensional analysis is that the lot number should be order 1 quantities. And also, as I mentioned before, we in general expect the presence of some classical logarithmic running that is induced by the diagrams with the appropriate degree of divergence. So diagrams that are generated by scattering of point masses. So they will induce the logarithmic running of lot numbers. And in the context of black holes, we can calculate the scattering amplitude in EFT and jar and actually test these results. Or we can solve the static tidal problem in the context of the Newtonian potential. And then we can check these expectations. And in fact, none of these expectations are true. So what we actually find is that in 4 dimensions, the lot numbers are identically 0 and they never run. Now, if you go to higher dimensions, then their behavior will depend on this quantity, L hat, the generalized angular momentum, which is the usual angular momentum, the usual L, the orbital number, divided by d minus 3. And so here I'm showing you general expression, but this expression takes the following. It behaves like this. When L hat is integer, it goes to 0. So this is always the case in 4 dimensions because d minus 3 is 1. Then if L hat is some generic number, which is not integer, not half integer. This is just some number. And then if L is half integer, you find a divergence. So the now, once you renormalize this divergence, you will see that the log numbers there will be some logarithmic contribution. So log numbers will exhibit logarithmic running. And all this behavior, both in 4 dimensions and higher dimensions, seems very unnatural from the point of view of dimensional analysis. So this kind of motivated the search for hidden symmetries in this problem. Well, I can say a few words what happens in the context of Kerr, but maybe in the interest of time, I'm going to skip this and mention this only later. Well, the thing that happens for Kerr is that you need to worry about the dissipation already even for the static problem, just because of the co-rotation, you will have some dissipation even in the static regime, because the rotating black hole will see static perturbations as time dependent. So it will start absorbing quanta from them. So you need to worry about this. But in principle, yeah, there is a way to account for that in the EFT by coupling your gravity to some internal horizon degrees of freedom and then matching the 2-point function of this horizon degrees of freedom. And you can do so, for instance, by calculating the absorption cross-section. All right.
You have 30 minutes.
I think I have also like 20 more slides or something. Okay, well, good. So what happens for Kerr black holes is that you don't have the spherical symmetry anymore, right? So now you only have the azimuthal symmetry, U1. So now you need to appropriately modify your operators, right? So they're not SO3. So now log numbers will become tensors. So this is the first thing you need to worry about. And the second thing you need to worry about is this dissipation that turns out to be important. This is because when you calculate, you have this contribution from the tree level counter term, but also if you have your graviton coupled to some horizon degrees of freedom, there will be a 2-point function of this horizon degrees of freedom that will contribute to the same scattering process. And in fact, this will produce the inelasticity. And you can do this calculation and you'll see that this absorption cross-section will be proportional to omega minus m capital omega, where capital omega is the angular velocity. So this is because you can effectively write this 2-point function in the t space. You can write this as an action of some time derivative in the co-rotating frame that in the usual asymptotic frame will be dt plus omega d5. So you can account for co-rotation. You see, like this will renormalize kind of the log numbers already in a static regime, right? Because the Eugen order effect here is kind of static. And this is something that was very confusing. So without EFT, it's very hard to kind of easily separate between these two effects. But in EFT, it's super easy, right? One is one diagram, the other one is another diagram, okay? And there was some confusion in the literature about Kerr log numbers. There was like a big argument in the literature whether they're 0 or not. But once you actually account for this dissipation, then you can derive the result that for Kerr black holes log numbers are 0. So we have obtained this result using this worldline EFT, and this also agreed with other physical arguments presented by Hornchen Chia, my collaborator. And basically, we all kind of converged to the log numbers are 0, and this was very timely because this result later on was used for the neutron star black hole merger event observed by LIGO in their data analysis. Because when you produce the waveforms, you need to decide whether you are going to have the log number form or not. So this was one of the applications of this EFT that was kind of powerful, because it's only in the EFT that you can clearly sort of separate these two effects. And in JAR is much less obvious. All right. So a quick comment that I have about this DLN, dynamical log numbers, is that in principle, there is this problem that log numbers could run. So it doesn't happen to be the case for the linear order log numbers, but then this does happen for the next to linear order operators that correspond to the time-dependent tides, or they're described by dynamical log numbers, basically log numbers that have some powers of frequency in front of them. And in this case, the EFT gives a very consistent definition for those log numbers as well, through the matching, through the this action principle plus the matching. Yeah, this is something that's very hard to account for in the context of usual jar, just because this division into source and response kind of breaks down. But in the EFT, you can easily do that. And basically, if you want to describe dynamical tides, you need to write down the scalar order operators on the word line. For Schwarzschild black holes, the linear order operator will look like this. So it will be E dot squared. So dot is the time derivative in the with respect to proper time. So time derivative in the local frame of the word line. And also in the context of Kier, you can also write down this operator, and this is a conservative operator, right? So it's even under time reversal. And you can, again, use this scattering amplitudes to calculate these operators, and they're running, and we have obtained that they're non-zero. And so we calculated they're running, and also we did a full calculation for the full scattering amplitude and fixed not only the running but also the constant piece, the scheme dependent piece for for this problem, like this was for the phi dot operator for the scalar kind of gravity for the scalar for the scattering of scalar fields. So this is like an analog of this operator in full jar. So you can do that for black holes. For black holes, you see like we have some fine tuning at leading order, but at next to leading order for dynamic Love numbers, there is no fine tuning, and everything happens exactly as expected from the Wilsonian naturalness. So Love numbers are non-zero, they run, and you can use EFT to account for this running. So I mentioned this naturalness several times. So why do we talk so much about this? Well, this is because in general, in physics, we can solve the problems, like many problems we can solve. We already know the answer for them, right? And the answer just comes from dimensional analysis. For instance, if I consider a dynamics pendulum and some parameters of the system, I can estimate based on dimensional analysis that the period of this pendulum will be just root of L over G, right? For instance, it will not depend on mass just because it's impossible in dimensional analysis. And the same logic should apply to the tidal problem in jar. So we would expect the Love numbers to, for a system of, for a compact body whose radiuses R and mass M, we would expect that the Love number will be defined by these parameters, maybe plus gravity, plus the Newtonian constant. So we expect the Love number to scale on dimensional grounds to be basically like order 1, to scale like M over R. Well, if you want to say that G is not equal to 1, then it will be M over R. But in fact, what you find is that it's 0. So the actual Love number for black holes is not given by the natural parameters of the system. It's given by something else. If you calculate then, if you ask the question, what will generate the first non-trivial Love numbers in pure gravity? So this will be a two-loop correction to the Einstein-Hilbert action. And the Love number will scale as the Planck length over the size of the compact body to the 4th power, right? So it seems that, well, normally when we calculate the dynamics of the pendulum, we don't need to worry about quantum gravity. But here, for perfectly classical tidal problem, the result, linear order result is given by quantum gravity. So this seems to be kind of very strange. So there has to be some explanation to that.
So is the answer correct, or is there some problem because you are not dealing with quantum gravity anyway, right? Just this element. Oh,
you can start. No, we can't. We always deal with quantum gravity as an EFT, right? For us, gravity is an EFT, right? So if you treat gravity as an EFT, there will be a two-loop operator that R cubed, like R mu lambda rho, that you contract with itself 3 times, and this will produce the following contribution. So this is the result in quantum gravity as an EFT. Is an effective correction to the jar. Okay.
So then the previous answer you have to me about whether you do have quantum is that quantum correction based on EFT is still quantum correction, it's not quantum correction.
Oh well, before we didn't consider this correction because before we were just doing usual jar, right? We were considering usual dynamical tidal problem. But now if you go beyond that and say, look, okay, let me consider now all possible corrections to jar, right? And now ask the question, at what point the Love numbers will be non-zero? The answer will be, okay, this will be the linear order contribution. Or if you ignore matter, if you have matter, then there will be some other scales in the problem. But again, they will come from some quantum effects, right? So the general point is that if you only focus on usual black holes, then the leading order of number will be generated by quantum effects. More questions?
Is it specifically quantum effects or higher dimension operators?
Well, at this point is a just higher dimensional, higher order operators in the Einstein field protection. But in general, we expect them. Okay, we generally expect them to come from quantum gravity, just because this is a counter term. The R cube is a counter term, two counter term for GR, right? If you start with GR,
Sure, but I mean, it could be present classically with a much larger coefficient.
right?
In string theory, if there's a separation between the string scale and the quantum scale.
Right. Yeah. Yeah, that's true. Well, but typically, again, when we talk about string theory, is also something quantum construction, right? Because here I'm kind of moving from classical Einstein field gravity, right? And now,
No, but that would be another scale all the way to.
yeah, if you have matter, there will be another scale. Yeah, here again, I'm saying that if you ignore matter for the moment and only focus on gravity, this is the guaranteed log number result that is there. At least it will scale like this. Of course, if you have matter, there will be some matter scales, right? You can have a tulip diagram that generates the coefficient from the R cube that comes from if you integrate out fermions, for instance. Okay.
I think now in string theory, there are tidal formations in
No, nobody looked at this, but yeah, if you start solving, in the stringy corrections to gravity, you start solving the tidal problem, you will find this kind of corrections in general.
types of A series, one of the A series paper series, they have string from like tidal effects. So at some point there was some debate whether aquaplane with interns. Something like this correction, but
Right, exactly. Yeah. People also consider, well, now they started, there was another related work, as you mentioned, about tidal effects in the presence of these higher order corrections. Well, in this particular case, I'm only focusing on this induced tidal response. Okay? So it's slightly different from the paper that you mentioned. All right, good. So in the last few minutes, okay, let me tell you what is going on with this problem. So, okay, as I mentioned, for us, GR is a UV theory. So if something like this happens, some fine-tuning happens, okay, and we have the UV theory, it's best to understand what is going on in the context of the UV theory. So from the UV theory, we need to understand what is fine-tuned in the black hole perturbation theory calculations. So this is the cartoon of the black hole perturbation theory. We have some small perturbation, like a Sneezen ant, that then perturbs the geometry of the black hole. Let's say we want to go for Kerr black holes, the more general black holes. And then the Sneezen ant will be described as a Klein-Gordon equation with the box operator calculated for the Kerr metric. And the first non-trivial observation is that for Kerr, the solution to the black hole perturbation theory equations will factorize, even though we don't have naively enough symmetries for that, but the radial coordinate and the polar angle will factorize. And the radial wave function then will satisfy an analog of the Schrödinger equation. So basically, you will have some kinetic term with two derivatives of r. There will be some weight that depends on the inner and outer horizons. There will be some potential, and also there will be some eigenvalues that for small frequencies, basically these eigenvalues will reduce to L+1. So we're always kind of in the regime of small frequencies in the context of gravitational astronomy. Now, as I said before,
can you explain the cartoon?
Okay, good. This cartoon was so Vishweshvara, he introduced quasi-normal modes, right? Okay, this is how you generate quasi-normal modes. You have a black hole, you sneeze on them, the black holes start ringing. But like the low frequency equation that describes quasi-normal modes will give you a lot of numbers because of all perturbations, right? It's perturbations for all kinds of. This is the equation for all kinds of perturbations. So yeah, this is the explanation of the cartoon. So for us, this should be an ant that sneezes static perturbations. Okay.
Contiguous one.
Huh?
You can take your time.
Okay.
12:30.
Okay. Thanks. 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 Right. Yeah, the simplest calculation you can do in this context, you can calculate the you can solve the problem for exact static perturbations, and this problem you can solve exactly in GR. So the radial wave function then will look like this. It will be expressed in terms of the Gauss hypergeometric function. So this is a full kind of result. But the most crucial point about this is that when L is integer, this function is a polynomial in R. So it's a function of R. So at R going to infinity, I can sort of Taylor expand, and I will see that there will be only growing modes that correspond to different multiples of the season end. This is the tidal force of the season end, but there will be no terms that go like 1 over R, because this is a polynomial. So there will be no law of numbers. This is like an easy way to see in the context of Newtonian sort of gravity why the law of numbers are 0. Okay, so everything from this point of view, you see that everything is kind of depends on this statement that the solution, the static solution, is a polynomial. Yeah, basically this comment is that the same form will be true even when you consider the same problem at low frequencies. The solution will be very similar, just this z function will be different. So that means that for low frequencies that are relevant for the scattering problem, basically the story will be the same. The vanishing of law of numbers will be a result of the polynomial structure of the static solution of or like low frequency solution in this case. All right, in the context of scattering, now we cannot solve this problem for scattering problem in general exactly. Well, we can do so only using some sort of perturbative techniques. And well, basically the kind of perturbation theory that you need to do in this case is a near zone expansion. So in general, you need to split your Schrödinger equation into two regimes. In the near zone, basically you assume that frequency times the distance to the black hole is very small, and you can sort of build a perturbative expansion in the near zone. In the far zone, you assume that you're very far away from the black hole, so you can build a different perturbative expansion, and then you can match. And in principle, this near zone and far zone, they have huge overlap, so you can like take advantage of this overlap and match this at all orders. And this is how you can build in principle a full solution. But here the point is that it seems that the relevant regime here is really this near zone, because this is something that senses the black hole itself. And in this case, we can split the potential in the Schrödinger problem into two pieces. So one piece that kind of becomes dominant in the static problem. So when at low frequencies, basically near zone becomes infinitely large. So it counts both the horizon and asymptotic infinity. And then there will be a different term or correction that is relevant in the far zone that normally we sort of drop. So the idea of this near zone expansion basically is to split the potential into two pieces with some formal parameter epsilon. And then, if we only focus near zone expansion, we drop this term. And you can do that in multiple ways. But for your calculation to be consistent, the only requirement that you need to have is that this extra term that you're dropping is much smaller than this in this regime. And this basically also corresponds to multiple expansion. So in this regime, the field around the black hole would be described as a multiple expansion. And this kind of near zone, as I mentioned, the near zone expansion is exact at 0 frequency. There is one particularly suitable choice of this split. So here I'm showing you these functions V0 and V1 for reference. The relevant parameter that will appear here is beta, which is, well, basically the inverse of the Hawking temperature. Well, here I assume h bar is 1. So this is like a classical Hawking temperature. And in this case, you can see that a symmetry will appear. So I can write down a vector field of 3 vector fields, L0, L plus, and L minus, that will look like this. And then these vector fields will form an algebra. So this will be an Saussure algebra. So these fields will satisfy the Saussure to our commutation relations. And then these fields are also going to be regular at the horizon, which is nice because then they describe the physical solutions that are relevant at the horizon. And then you can rewrite this near zone Tikhowsky equation. This Tikhowsky equation is the equation for the Sneezing hand. So you can rewrite this as a Casimir problem for this algebra. And now you can see that it's great because we can extract all the solutions. You can build all the solutions using the algebraic properties and not solving the differential equations. So this is why we like symmetries. Well, at some point also here, I had a discussion, of the relationship between this symmetry with the KRCFT, which is kind of very similar. In the near zone, there is an extra symmetry. There's a cell to R cross cell to R that was done by Andy Strominger here and collaborators. But our symmetry is different because the KRCFT was only a local symmetry. It was broken by the periodic identification of the azimuthal angle. And the KRCFT symmetry didn't have a smooth shortcut limit. So for us, as I mentioned, the vectors are globally well defined. They're regular to the horizon, and also they have a smooth shortcut limit. So which is nice because now the physical solutions of black hole perturbations, they actually form representations of this symmetry, which was not the case for the KRCFT. So why this symmetry is great? Because now we can solve a black hole perturbation just like the hydrogen atom. There is a statement that the black hole is the atom of the 21st century. This appeared in many different articles and publications. Now we can make this statement actually very precise in the exact mathematical sense. We can use this extra symmetry that I call love symmetry. We can use it to solve a black hole perturbation same way as we use the hydrogen symmetries, the SO4, SO3 cross SO3 in the context of hydrogen, we can use to obtain its spectrum. Now we can calculate the spectrum of the black hole perturbations using the algebraic arguments only.
Let me mention one thing. There's something about the SL2R representation you mentioned. One sentence in the end of the slide.
Right.
So that's why spin 2,1. Just make sure that kind of the geometry using SL2R is it's a part of the spin 2,1 because like the Minkowski version of the three-dimensional Lorentz transformation is used.
Yeah, probably. I really forgot how to translate this to spin language. But the SL2R, maybe in the more geometric context, the SL2R is the isometry of the two-dimensional anti-de Sitter space. Okay, this is actually something that will be important when I discuss the geometric origin of this symmetry.
Two-dimensional ADS.
Yeah, two-dimensional ADS. So ADS2. This is the isometry of the ADS2.
The ADS2 show up because in this context, ADS2 shows up.
Yeah, why it shows up is kind of amazing. It's because this is because the black holes in 4 dimensions, like the charged black holes, for instance, they have the enhanced isometry in the near horizon region, which is ADS2. Love symmetry is a remnant of that that survives even beyond the scaling limit, beyond the chronology. So there is a very tight relationship between the two. Okay, so in the context of this representation theory, you can basically prove, you can build a, let's say, highest weight representation and prove that the left numbers vanish as a result of this structure. So, well, the structure of the representation is defined by 2 things, by the Casimir and by the lowest value of the eigenvalue of the L0 operator. So in our case, L0 is minus beta times dt. So the static solution has H0, well, H0. And coupled with integer L, this automatically means that the relevant solution will be part of the highest weight representation. So okay, let's build this representation. We start with some primary. So here I'm using L equal 2, the quadrupolar case. We start with some primary, V2. So it is by construction annihilated by L plus. And then we use lowering operators to build the whole kind of ladder of states. And the static solution will be one of these states in the ladder. And now you can start from the static solution and go up. You can raise it 2 times and get the primary. And if you act on the primary one more time with L plus, you get 0. So basically, this condition is written here. So if I start the primary and act, well, in general, this will be L plus 1 times. What I might find is 0 on the right-hand side. But then if you actually plug the explicit expression for the vectors, so this operator will be proportional to the L plus 1 derivative in coordinate r. So it means that this highest weight condition basically implies that V naught should be polynomial in R. So let me go back to our discussion of Love numbers. In general, we expect, so V naught is our, let's say, gravitational potential. So we expect this to be, on large scales, you have this tidal force, and then we have some 1/r tail that corresponds to the Love number. But in fact, this highest wave structure forces the polynomial expression for the wave function. So that means that basically, you find this is enforced by the highest wave structure, and hence the Love number is 0 as a result of this highest wave representation. And you can now also prove the same for other, in higher dimensions. You can also say that the properties of Love numbers, they are dictated by the representation theory. Also, the representation theory tells you something about the physics. For instance, in the context of Schwarzschild, the kind of ladder representation that you build will be finite dimensional. And this has to do with the fact that the black hole perturbations, they are regular both for the black hole on the black hole horizon and on the white hole horizon. For the Kerr black holes, they form an infinite, sort of infinite ladder, and you can construct a final, or you can do a coset and construct a Verma module that is, well, basically related. It's infinite structure. The Verma module is related to the fact that any physical solution will have singularity on the white hole horizon, and this is something that is a specific signature of the Kerr black holes. And in general, we can go to higher dimensions and also, map these properties of higher dimensional Love numbers, where they run, whether they are finite. You can map this also onto some structure of the representation theory. And we published several papers on that. So let me maybe skip this and go all the way to this geometric picture. So why do we have this in the first place? So to understand that, we can look at the charged black holes, the Reister and Nordstrom black holes, and we can consider their extremal limit. So when the charge of the black hole approaches its mass, and in this case, we also have the Love symmetry. And in this particular limit where Q goes to M, we'll see that the Love symmetry will actually reproduce the usual near horizon isometry. So basically, you can think of the Love symmetry as a broken near horizon isometry in the context of holography. So it has a well-defined geometric interpretation as well. And in fact, if you ask the question, what is the regime of the validity of this Love symmetry? Because I was making some approximations, near zone, small frequency. So if you ask what's the regime of the validity, this will draw you something that looks a lot like the phase diagram in the context of IDS CFT. So on the x-axis, I'm showing you the distance to the black hole horizon. On the y-axis, I'm showing you the combination of frequency over the Hawking temperature. So when the Hawking temperature goes to 0 and frequency is also small, the Love symmetry becomes an exact isometry. Now, if you go beyond that, if you go for some, let's say finite Hawking temperature, small frequency, and large distance, then the Love symmetry will be a symmetry of the equations of motion, provided that omega times r minus r plus is less than 1. And at finite temperature, this kind of corresponds to the regime of plasma in the IDS CFT context. So from this picture, you can conclude that Love symmetry exists basically as a consequence of the near horizon isometry. You can think of this as a spontaneously broken near horizon isometry at finite temperature.
You need to add charm, right? To have hydrogen Newman.
Right. So for
don't see this
no, for Kerr, yeah, that's a good point. For Kerr, we see exactly the same thing. We found this Love symmetry construction for many different systems.
but the coincidence with the isometry.
Yeah, okay. Here the story is slightly more interesting because in the context of Kerr, in principle, you can build an infinite dimensional extension of the Love symmetry in the Kerr case. So you can build a more general group, SL2R semi-cross U1, where basically you start with the usual Love symmetry and add different vectors of this type. And then different subgroups of this bigger group will give you, one of them will give you the Love symmetry, the usual Love symmetry. The other one will give you this Starobinsky symmetry that we also discovered along the way that is relevant for the absorption properties. And the third choice, the third subgroup in this infinite dimensional group will give you the Kerr isometry. So a lot of symmetry, but it does not exactly reduce to the in the Kerr case, does not exactly reduce to the near horizon isometry of Bardeen and Horowitz, but one of the subgroup of the generalized flow symmetry does. So you can use the same principle to build like a larger group.
And do you have an intuition why you need to add charge to have it exactly?
I feel like it's just because for a charge case, you don't have that many parameters, and I said physics is much simpler. Yeah. So yeah, everything simplifies in the charge case, but the Kerr case is more interesting. And also, yeah, let me mention that I think that there are other works done by Lemhu and collaborators, and also here by Uri and Alfredo that basically found some other hidden symmetries in this setup. So the story is incomplete. I feel like the whole symmetry structure of the Kerr black holes, well, contains many different things. All right, and maybe the very last thing that I'm going to tell you is, whether we're happy now, whether we solved the naturalness problem. I would say yes and no in the following sense. So on one hand, we have some symmetry that imposes selection rules, and these selection rules, they ultimately force a lot of numbers to vanish. But those selection rules, they appear at the level of the UV theory. So from this point of view, it looks like a UV miracle. And you can think that to see what the point here, maybe we can go back to this multiplet of the different states in the black hole perturbation theory representation. And this Raman operator that we have, they produce states whose typical masses, whose typical time dependence is of order of the black hole mass, right? So when we talk about flat numbers, we're interested in the EFT in the regime where the typical, let's say, energies are lower than 1 over RS. But here, the symmetry is a symmetry between the static state and the very massive states that you have integrated out in the EFT, that are not present in the EFT. So in this sense, the love symmetry mixes IR and UV states. And from the point of view of the full IR theory, you will not be able to see this just because you have to integrate out the symmetric states. So I think it's a very interesting example. It's different from the Hooft notion of naturalness. It's like a mixing, IR-UV mixing type of naturalness. But I think that in generally, I find this very entertaining also to think that some sort of IR-UV mixing can be used as a solution to the other naturalness problems, such as the cosmological constant problem.
Excuse me.
Yes.
Like which part reflects the IR and which part is UV? Maybe basically.
Right, very good. So imagine you start with a static solution. So static solution by definition doesn't depend on time, right? So it's like massless in this context, right? So there is a state that is massless. Now you apply the Raman operator, right? It will generate a state whose mass now, typical frequency here, will be of order of the black hole mass. Well, basically these other states here, they correspond to kind of quasi-normal modes, right? So quasi-normal modes are beyond the EFT because their typical energy scale is greater than, they typically scale like the mass, right? Whereas your EFT is only applicable to low energy, so the frequency is much lower than 1 over the Schwarzschild values. So this is symmetry from the point of view of the EFT between the EFT states and the massive states that are not within the EFT. So in this sense, this is the IR-UV situation. Yes. Well, no, we don't really get negative constraints. We get some of the states that we have. They have like a large and positive frequency, so like plus MT that grow with time. Yeah, this I think what you refer to. So they correspond to the situation when the like a source keeps pumping up energy on the black hole. So it's a still kind of physical solution, right? So we don't really care about them. Like these solutions are not relevant. Okay, maybe they are to some extent during the spiral phase, but in the adiabatic regime, this post-Newtonian phase that we're looking at, solutions don't play a significant role. So they're still part of the spectrum because they're a solution of the original problem. But in some sense, they're physical here, so don't worry about it. Modulo the fact that the solutions are approximate because I've been them in the years of approximation. So they receive corrections. But in principle, yeah, they are kind of physical solution of the equation. All right. So yeah, there are some practical applications of this. We can basically, once we have symmetry, we can perturb upon it and come up with some perturbative way to solve the Tikolsky equation. Okay, this is some practical application that might be relevant for future experiments such as LISA. But let me skip over that and go to the summary of my results. So I hope I have convinced you that love numbers can be nicely defined in worldline effective field theory as Wilson coefficients, and the best way to extract them is to calculate scattering amplitudes. Then I have introduced, well, I said that the black hole love numbers are zero. I introduced a symmetry explanation, love symmetry that explains the vanishing of love number. And this love symmetry is very tightly related to holographic constructions, to the near horizon isometries of two-dimensional black holes. And also there could be some practical applications in terms of new systematic way to calculate precision waveforms for gravitational wave signs. So I think I will stop with that. Thank you so much for your attention.
Thank you, Misha, for the talk.
Yes.
So I wonder which order of
Okay, in terms of the, okay, let me say this, that, yeah, this is when we, I think, go back to this near zone expansion. So love symmetry only exists at leading order in the near zone. And next to the order doesn't exist. But it makes sense because we see that only the lowest order Wilson coefficients are fine-tuned. And higher order Wilson coefficients that depend on frequency are typically not fine-tuned. Okay? So there should be no symmetry explanation. And that's why it kind of makes sense that love symmetry only appears approximately like for very small frequencies. Okay. One of the future directions that was very fun for us is to look at different other spacetimes, whether they have love symmetry or not. So I discussed this, love symmetries, extended love symmetries in 4 dimensions. But if you look in higher dimensions, then this has become really fun. For instance, if you consider the love symmetries of 5-dimensional rotating black holes, the Myers-Berry black holes, then you can find that there are totally different fine-tuning conditions that are, very different from the static case. It's like, for black holes, for instance, in 4D, for K black holes, love numbers are 0. For Schwarzschild black holes, love numbers are 0. You might think that it's kind of the same thing, right? But in 5D, this is not the case. And if you have for certain quantum numbers, or for certain perturbation numbers, you can have static love number 0 for static black holes, but then for Myers-Berry black holes they will not be 0 anymore. So there are different types of fine tuning. So this was a lot of fun to play with, and also we're now looking into the love symmetries of the p-branes, because in the context of the p-branes, first of all we can find like more complicated symmetry structures. And then they are more closely connected to the near horizon isometries of the p-branes. So I feel like now we make a statement about the connection with the isometries more accurate in this context. So from the theory point of view, I would say that those are the most 2 interesting future directions.
How would you measure the dynamic development, for instance, in extreme mass radiation stuff?
Yeah.
Very, very small. There is no tidal deformation, but you will still have some implications on the units. The same way, there are implications on the waveform just by doing the symmetry. So can we say something about just extreme mass ratio?
Yeah, it's exactly what you said. For the extreme mass ratio, the point is now, well, again, you have a binary problem. Your waveform will depend on the love numbers, right? And there will be a way to extract them.
Is there something as sharp as the amplitude? Because this motion also is fed by perturbation.
Yeah, you can solve this by expanding over the mass ratio here, right? But this is a different dimension, right? Because for us, these love numbers, they kind of exist in the post-Newtonian regime for any masses, right? So in this case, like having the mass hierarchy doesn't really help you much in this context. it doesn't help you improve the calculations because this post-Newtonian setup already is kind of okay for any mass ratio.
But the computation you do still have some perturbation. There is some lack of perturbation here. In the UV theory.
Oh, in the EVT. Oh, yeah.
There's no perturbation.
Well, this is when we're looking at one body, right? I mean, this picture makes it okay. So the extreme mass ratio story is good really for studying log numbers of individual bodies, right? Because in gravitational astronomy, what we actually measure, coming back to my previous slides, we measure always a combination of log numbers of two bodies, right? So sometimes it's hard to break degeneracy. So your waveform is sensitive to the, let's say, mass-weighted combination of log numbers of two bodies. Now, in this case, you can take advantage of this, mass ratio story, and then you will be more sensitive to the log number only of the big body, right? So you can break the degeneracy here more efficiently. That's right.
If we have no more questions, it's time to be sure again.
Are there any questions maybe on Zoom? No, I don't see any.